Today I would like to tell you of a problem I've been working on in the past few years, which is address impurities in an ideal Fermi gas, which it's not a few body problem. It's, if you want, a many body problem, but can be formulated in the language of n+1 body problem with n larger than 1 or much larger than 1. And okay. So this talk has quite some overlap with the talk that Christian Trefker gave at the very beginning of this talk. I think it's been the second talk. He was talking a very similar physics. So for those who were there already, maybe they're familiar with some of the stuff I will talk today. Okay, so brief introduction, a few slides on introduction on why this problem can be interesting. So there's been many experiments in the past years on quantum mixtures in condensed matter. I mean, it's much more general than ultra-cold gases. But in ultra-cold gases, of course, we can look at mixtures of bosonic and fermionic atoms. So in many experiments in the world, but also this is a much older problem that's been looked in the 70s in the context of liquid helium. And it goes up to also other phenomena like neutron stars and quark-gluon plasmas. And other interesting mixtures can be considered, for example, spinor gases, in which you have a gas containing many spin components, or spin liquids can be, or unconventional superconductors, where you have mixtures of different superfluids with different parities. Or all these systems, despite the very different microscopic origins, at low energies, can be often described by so-called emergent many-body theories, which show a significant degree of universality. This, if you want, is summarized in a couple of plots here. So, for example, here you have a plot of temperature versus pressure, and you have the ultra-cold Fermi gases at nano-Kelvin temperature down here, helium at kelvins, neutron stars up at 10 to the 8 and quark-gluon plasma at 10 to the 12. So there's almost 20 orders of magnitude difference in temperature between these systems. But on the other hand, there are similar transport properties in some cases. For example, this is a plot of the ratio between the shear viscosity and the entropy density close to Tc. And what you can see is that this is not a logarithmic scale. This is a real scale. And so this system have very similar, this quantity behaves very similarly in the, for this very different systems. Okay, so I've been trained in ultra-cold gases. So what I find very interesting on these systems is that there are extremely they've been often described as quantum simulators, if you want, because there are so many parameters that one can actually change. So one can play it easily with the chemical composition of the gas, can change the temperature, the interaction strength. Or one can impose periodic potentials very similar to the one has in solids. Or can play with the physical dimensions, so constrain the gas to 2D, 1D, or even point-like sites as one has in a crystal. One can introduce exotic coupling, so S wave, D wave, P wave, and higher ones if interested. Can consider scattering in very different partial waves. Can introduce spin-orbit couplings. One can look at the dynamics of these systems. One can introduce, the nice thing of this system is that they are basically free of any disorder, but one can introduce controlled amounts of disorder. And one can also engineer periodic driving, which this is a topic that has been worked a lot in the group where I work, at Maciek Levenstein at Institute of Photonic Sciences. So one can impose a frequency or amplitude modulation to the optical lattice to induce interesting phenomena. Okay, so I will be mainly focusing on Fermi-Fermi mixtures. So this is a plot that has been, this is a system that has been looked extremely intensively in the past 15 years. So this is a plot of the so-called BCS to BEC crossover, which was developed many years ago, but then has been thoroughly investigated in the context of ultra-cold atoms. And so it's one tunes at very low temperature, one tunes the interaction from weak to strong. One has this continuous transition from continuous crossover from a dilute, a gas of very large pairs to as the interaction is weak. This is a BCS superconductor. And as the interaction is tuned, the pairs start to shrink. At this point, the interaction, the distance between the pair radius becomes comparable to the interparticle distance. And for very strong attraction, the spin-ups and spin-down bind into molecules. Oh, sorry, I didn't say it. So red and blue are spin-ups and spin-down. So I'm talking here of a spin 1/2 Fermi gas. So at very strong interaction, the spin-ups and spin-down bind and form deeply bound molecules, and this becomes Bose-Einstein condensates of molecules. So at very low temperatures, there is crossover, and at higher temperature, there is, I would say, this is maybe a bit more discussed, this part of the phase diagram, but at least the lower part now is quite well understood. So this is a situation in which the number of spin-ups and spin-down is the same. And then a bit later, people started to wonder, okay, what happens if we start to imbalance the gas, in the sense that we take that the number of spin-ups, for example, is larger than the number of spin-downs. This is a very nice experiment in the group of Martin Zwirlein, and in which at MIT, in which they looked at, they set the gas in rotation, and they said, okay, if the gas if the number of particles in spin up and spin down is the same, one observes a very nice vortex lattice. So this is superfluid gas, but it's so since it can sustain a vortex lattice of quantized vortices, this means it's a superfluid. But then as one introduces a larger and larger spin imbalance, one sees that at some point the vortices disappear. And this, in some sense, signals the transition from a superfluid to a normal gas. So here one has basically a large number of spin-ups and very few spin-downs. And there is a breakdown of the superfluid.
This is lithium-6?
This is lithium-6, correct, yes. Okay, so I will be interested in, if you want, this last figure here, in which we have extremely many spin-ups and very few spin-downs. So this is what I describe here as red and blue particles. And so this is a very imbalanced Fermi mixture. And if one has, for example, attractive interactions, one has, as I will discuss in this talk, one has the formation of so-called polarons. So these are dressed quasi-particles in which the blue particles are dressed by excitations in the majority gas, and they basically form a quasi-particle, which I will call polaron. This happens for attractive Fermi mixtures, but also for repulsive Fermi mixture, as I will discuss later. For repulsive Fermi mixture, there is also a very interesting other phenomena, that is, what happens is the repulsion becomes very strong. Because you can imagine that if the repulsion is very strong, the energy is minimized by confining all the red particles on the left and all the blue on the right. And so there is a competition. In a repulsive Fermi gas, there is a competition between repulsion and Fermi pressure that instead tries to expand to keep the particles as far as they can. And this is a very old problem that nonetheless is still open. In the sense, it was formulated already in 1933 by Stoner. It was called itinerant ferromagnetism. So it's a ferromagnetism itinerant, coming from Latin, means, I mean, particles are moving away from each other. And so the question is whether this can actually be realized in any system. And apparently, I mean, there were some claims some years ago that this had been seen in a Fermi gas, but actually it became clear that this was not the case yet. So at the moment, this is still an open question whether such a system can be realized. Okay, so coming to the outline of the talk, this is what I will consider. So I will consider one spin-down impurity in an ideal Fermi gas at T much smaller than Tf. Let's say for all purposes, I will actually remain to T equal to 0. And I will consider a Fermi, I mean, usual state in a ultra-cold gas. So this means that particles can be, interaction between particles can be considered as contact interactions. And I will restrict here myself to S-wave interactions, because we are at very low temperatures, so spin-ups and spin-down just interact with S-wave contact interaction. And I will consider, okay, first I will consider the S-wave case, then I will also discuss the P-wave case, in which is a bit more exotic. So let's say the first case has been already realized experimentally. I will discuss an experiment that we have been investigating. The P-wave case is actually more open, and so we made some theoretical predictions, and it would be nice if an experiment will come soon to confirm them. And then I will discuss how this theory can be applied to understand more the itinerant ferromagnetism problem, if there is time left. So just one more slide for motivation. Understanding the properties of single impurity in a Fermi gas provides quite some insight on, for example, the phase diagram of a strongly interacting Fermi gas in the imbalance, at least in the imbalance case. But so let's say understanding the property of single impurity actually gives access to the phase diagram even for a finite number of particles, based on the concept of so-called Fermi liquids. So if one is able to understand the property of one particle, then we can what one can show is that the interaction between quasi-particles are actually very weak, and so one can consider the gas in which one has limited the number of impurities as composed of quasi-particles, non-interacting quasi-particles. And one can investigate also the coherence properties of these quasi-particles, and one can look at how this quasi-particle decay into other types of quasi-particles. And then if one is interested in P-wave, as also Jesper was discussing the other day, a P-wave superfluid could be polar or chiral or as topological excitations. So it would be very interesting to understand, I mean, the basic building blocks of a P-wave interacting Fermi gas in order eventually to arrive to a superfluid of P-wave pairs. And we will see whether it's possible to go beyond some of the limitations that are presently prohibiting to investigate itinerant ferromagnetism in ultra-cold gases. So if you this is a slide of advertisement. This is a review that I've been just writing in collaboration with Georg Brun and Matteo Zaccanti, which covers basically most of the topics we have. I will talk today, plus many more gory details on all the theoretical models and experimental probes and experimental results that have been collected in this field. It covers also some more technical parts on or extensions of what I'm just talking today on mass imbalance and reduced dimensionality. This is a topic that Jesper and Mera have been working a lot in the past years. So what happens to this, the physics I'm discussing when you go to 2D or 1D, or when the particles, some of the particles are very, I mean, the impurity is very heavy or very light. And also a lot of details on the decay processes. Okay, so coming to the first part of the talk, so S-wave interactions. Okay, so just couple more slides on the quasi-particles entering this. That will be basically the main topic of this this talk. So what is a many-body system? It's this couple of images I like very much from this book. So what's a many-body system is anything from electron in a metal to atoms in a solid to angels on pinheads. So basically something very complicated that's hard to describe, in particular in which the trajectory of the particles scatter a lot between each other, and the trajectories are extremely involved. And the idea of Landau was actually, why should we care about the real particles? Of importance are the excitations in these gases, and this can be described in terms of quasi-particles. So a quasi-particle is something that behaves simply, let's say. And in this book, there is an analogy. So if a real particle is a real horse, a quasi-particle is a horse running in a desert. So it's something that gets covered by a cloud of excitations, and these excitations. This quasi-particle is basically a free particle, but under quotation marks. So it still retains the quantum numbers of the original particle, but it has a renormalized mass, which you can think of as the cloud of particles sticking around the horse. It has a chemical potential, that's the binding energy between the cloud and the ideal particle. It has shielding interactions because these quasi-particles have troubles to see each other and interact because of the cloud surrounding them. And it has a lifetime because this cloud can detach from the particle and fall down. So what does this mean in the context of our problem is, as we will see, there are three possible states. So if in the absence of interaction, we just have one impurity sitting in the middle of a Fermi gas, and the red particles are undisturbed by the blue particle. But if you switch on interaction, what you can have are, in particular, if you switch on repulsive interaction, what you can create is basically a hole in the Fermi gas. And this is what I will call a repulsive polaron. Or if you switch on very strong attractive interaction, what you can get is a bound state between the impurity and one spin-up particle, which basically they go and form a molecule, and they leave a hole in the Fermi gas, because now the spin-up particles are no longer n, but there are n minus 1, because one particle has been bound into the molecule. And for a slightly weaker interaction, or still attractive but slightly weaker, one has the formation of a so-called attractive polaron. So, and as you will see, this free situation are actually realized. All free situation can be analyzed and visualized actually in a Fermi gas. Okay. In particular, this is the, if you want, a plot of the spectral function that I've been investigating in collaboration with the Innsbruck group in an experiment that has been done a couple of years ago. So what they were having is a lithium Fermi gas mixed with a potassium Fermi gas, and they took a regime in which they had about 10 to the 5 lithium atoms and 10 to the 4, a few 10 to the 5 lithium atoms and a few 10 to the 4 potassium. So let's say 10% ratio. And the mass, so the potassium acts as the impurities in this case, and there is a mass ratio of impurity over bath of 40/6. And one important point in to understand the quantitative details of the experiment was that the range of the interaction, which I denote here by K R star, but if you want, R star is related to the usual effective range by minus RE over 2. I will come to more detail on that, but so this means that the effective range is actually plays an important role in the experiment. And so this is a plot of the spectral function. So here you have the Feshbach resonance, so going from BEC to BCS side, and at negative energies there is so on this side the interaction are attractive, and you have the spectral function displays a narrow peak, which basically corresponds to the attractive polaron. So this is the attractive branch. And what one sees on the other hand is that at some point there is another solution, which is the molecule solution, which has a lower energy than the polaron. So at this point there is a so-called polaron to molecule transition, because the ground state of an impurity goes from being a single particle, polar fermionic, if you want, quasi-particle, to a bound state, bosonic quasi-particle. So there is a change in the properties of the ground state excitation, or the ground state in the ground state, which is basically here it's a fermionic quasi-particle and here is a bosonic quasi-particle.
What's the scattering length here for what system?
So the scattering length is given here. So this is -1 over KFA.
No, but A is for lithium, for potassium, or for lithium potassium?
Oh, sorry. So these are identical fermions. So the lithium-lithium scattering length is 0, and the potassium-potassium is 0. So this is the lithium-potassium scattering length.
So why the bound state doesn't appear when the scattering length is infinite?
Because this is a many-body state.
No, but you said the molecule appears much earlier than 1 over A is 0. So the molecule appears as you only have the bound state between two atoms, right? So you don't care
But this is not a bare. This is, I mean, this is not two particles in vacuum. This is a lithium potassium. So you have many atoms of lithium and many potassium. And if you want, this is a plot for one.
molecule then.
Sorry.
What's the difference between the polar and molecule then? Because you're talking about the molecular state, and you're talking about.
So okay, what I'm.
What's the difference?
So the polaron. So okay, maybe there is a misunderstanding in the terminology. What I'm speaking is not a bare molecule, is a dressed molecule. So this molecule, you see, it's not just a bare molecule, but it has actually pushed away the other particles around.
So how you define it?
It's the
What's
pole.
the difference from the regular traction?
So what is the difference between these two states, you mean?
Yeah. Exactly.
So they appear as poles of two different integrals equation. One is a one-body integral equation. I mean, one is an integral equation describing.
No, but physically, what's the difference?
Well, actually, how do you distinguish what is molecule, what is attractive polar?
Oh, I'll have a beautiful image, experimental image that shows what is the difference. If
But
you want.
probably you calculated some.
Yes. Mhm.
So, what is the difference?
So one,
Actually,
I mean,
it seems that it may be, well, this picture doesn't explain the difference.
No, this picture is an illustrative picture. I will come to the calculation in a short while.
Well, okay.
Okay. So, but basically, I mean, the short answer is that this comes out as if you want, you can write down a variational ansatz in which you add one particle to a Fermi C, and you dress it up with a particle Hall excitation. Well, here you write an ansatz for a molecule in an n-1 Fermi gas.
But
and
those are theoretical models different which are approximate. It doesn't tell about the physics.
No, but, I mean, you can write, so you have an Hamiltonian, which is an Hamiltonian of spin up and spin down with contact interactions. And you can write down two different ansatz. One is an ansatz in which you add one impurity to a Fermi gas, of an unperturbed Fermi gas. And one is an ansatz in which you add a spin up and a spin down to
That was clear, but you have two uncontrolled approximations.
Which are?
Which you just described. You see, so which one?
What is uncontrolled? What is uncontrolled in
So
the?
what's the correction to that?
But to what? What is uncontrolled in?
The same. They should give the same result if they are both correct, but they don't.
No, they describe two physically different excitations, and in particular, two different limits. So one is a fermionic quasi-particle, and the other is a bosonic. So if you want, in the asymptotic cases, so when A goes to, when 1 over KFA goes either very large or very large and positive or large and negative, these two quasi-particles become the free particle interacting with weakly interacting with the Fermi gas. So this has energy 4 pi a divided by m. And this, the dashed line here becomes the energy of a molecule. So h bar squared over 2ma squared. Minus the Fermi energy, because you have removed one particle from the Fermi sea in order to bind this molecule. So these two excitations are very well defined in the limit, in the non-interacting limit of either a very small and positive, or very small and negative. So they are two completely different excitations, which are orthogonal. I mean, one is a one particle object, the other is a two particle object.
Pietro, if I sort of think about this as a two-body problem, and I see sort of curve crossings, right?
Mhm.
And sort of trying to draw your solid line and your gas
Mhm.
line. Then in the two-body problem, I would always ask the question, if I look at the next order correction, is there some level repulsion, and do your curves actually sort of repel each other, and do you have a curve that goes this way and then up? And then there's a little bit of an energy splitting.
I think so. The answer is no, in the sense that these two excitation are actually two different objects. So there is no coupling between the two objects,
Right.
because one describes a fermionic object and one describes a bosonic object, which is dressed by excitation in the system. So what will happen when if you go to a higher and higher order should be a smoothing of this crossing, but there is no coupling between. I mean, what you can do is basically go to the next order. I did this in some.
About excitation, you should talk about the ground state.
So
happens
what
to
I'm
the
saying-
ground state of the system?
The ground state of the
Change
system.
scattering length.
Sorry.
When you change the scattering length from the BCS towards the Fesmer resonant, what happens to the ground state of the system?
I mean, this is what happens to the ground state of the system. So there is.
That's critical, on a critical point.
So.
Or phase separation.
So this is a one particle problem. So there is one impurity in a Fermi gas. So there can be no phase separation. But it's true that the nature of the ground state changes from being bosonic to being fermionic. So there is a change in the properties of the fundamental quasi-particle, the ground state quasi-particle, if you want.
So then is it, maybe we can postpone this to the study.
Okay. Okay, in particular, there is also a repulsive branch. So if you look at positive energies, okay, sorry, and I didn't say this is the energy of a ground state molecule, but actually the molecule is formed by taking one particle from the Fermi sea and binding it with an impurity. So since you can take actually any particle in the Fermi sea, from the one at the bottom of the Fermi sea to the one at the top of the Fermi sea, this is actually not just a line, but it's a continuum, which is drawn as this shaded gray area. So there is a line excitation, if you want, a sharp excitation, which gets a broadening when it enters here. And there is always a broad continuum appearing in the middle. And at positive energy, there is another excitation which can be understood if you go to the very left limit of this plot, where the scattering length becomes small and positive. So again, there one has the situation of a particle interacting with just a weak repulsive interaction with a gas. So if you want the impurity, the energy of the impurity in this limit is 4 pi a h bar squared divided by m. And then as you approach the Feshbach resonance, this remains, is a sharp line, but gets a slight broadening because this quasi-particle actually can decay to lower states. And at some point it becomes undefined when the line comes too close to the resonance and it gets a broader and broader width.
Excuse me.
Yes.
I don't understand. Why this molecule whole continuum is limited from above?
Because this height here is EF. So you can take, going back to this picture, the particle that you bind to the impurity can come actually from any point in the Fermi sea, from the bottom or from the top. And if you just work out through the calculation, this means that the energy of the molecule can actually vary by basically EF.
Maybe this will become clear when you explain how you actually calculate this, right?
Yeah.
You have two different ansätze for the ground state, and they're not necessarily the
Exactly.
solution, right?
Okay, so there is a repulsive polaron, which is it's intrinsically metastable, exactly because it can decay either in this broad continuum below here, or even by a many-body process into this other well-defined excitation or well-defined quasi-particle immersed in a continuum here. Okay, so here comes the ansatz for the polaron. If you want, so this is the physical picture again. So if you have one impurity injected in a Fermi sea, the Fermi sea is depicted here as a gray area. And you have, what the impurity can do is scatter and create a particle and a hole in the Fermi gas. And then the particle and the hole propagate inside the Fermi sea. Q is smaller than Kf, K is larger than Kf. And so by momentum conservation, impurity needs to keep P plus Q minus K. And at some point, so they propagate in this fashion, and at some point the particle and the hole recombine and the impurity goes further. So if you want to describe such a process, what you can do is take an unperturbed Fermi sea or an ideal Fermi sea at t equals 0 with the n particles, and add one impurity with the spin down at momentum p with a certain amplitude phi p. And then you can dress this excitation with particle and holes. So here you have, this is the impurity. And then you're creating a particle and a hole on top of the Fermi sea, and this happens with this amplitude here. And again, so the Q is restricted to smaller than Kf, and K is...
You can go high in that expansion.
Yes, you can, but as I will show, already at this level, the agreement with diagrammatic quantum Monte Carlo, which is believed to be exact in this problem, is to be within 1%. And
Depends on the strength of the interaction.
no, all across the regime in which this quasi-particle is well defined. That's actually why I find this problem very interesting, because at odds with similar techniques which I've been using in the context of balanced Fermi gases, so where you have an identical number of spin ups and spin down, what I will be using basically is forward scattering.
The problem is, let's assume I have a room full of air. See, those dilute, there is no interaction.
Yes.
I send a projectile. It will disturb the air here, all across the room. You see, when the room is bigger, it will disturb it all the way to the end. Here you say that it will disturb only at the beginning when the particle enters the room. I don't find it believable.
No, what I'm describing here is the processes entering the self-energy. And I agree with you that you can continue this expansion to higher orders. But it has been shown in invariant contexts also. Mera and Jesper did a lot of work on this. And what you can show is that actually the higher order corrections, basically there is always two terms that cancel each other. The leading order terms in the higher order expansion cancel each other. And indeed, you can show that this very simple approximation, I agree with you, it comes to within a few percent from exact quantum Monte Carlo and also experiments, as I will show you.
Is there an explanation for this? If there is such an almost exact cancellation, there has to be a reason for that, right? That's not an accident.
Yes. So the idea is that, okay, maybe it will become clearer when I draw self-energy. And
okay, but if it
Okay, so a similar wave function can be written for the molecule, but except that now here what you have is a Fermi sea with n-1 particle, and what you add to the unperturbed Fermi sea is directly a spin up and a spin down with total momentum 0. And then you dress this with quasi-particle excitation. So, but what is important is that the unperturbed part of the two ansatzes, the polaron and the molecule, is fundamentally different. One is a single particle on top of an ideal Fermi gas, and the other is two particles, spin up and spin down, on top of an unperturbed Fermi sea. Okay, so how to extract these quasi-particle properties I've been talking about. So one can, the self-energy of the impurity is given by an integral over the whole momenta on top of the T matrix, if you want. The energy of the two polaron is given by the real part of the energy of of a polaron with P equals 0 is given by the real part of this, because this is the shift in energy. The residue, which I will discuss later, but it's basically how much the quasi-particle looks like the real particle, is the overlap between the two, is defined in this way, again, through the self-energy of the impurity. And the effective masses of the polarons are given by the standard formula again. Okay, I won't go into too much into the details of the molecular equation, but this is given here. So it's an integral equation, and the energy of the molecule are given by, so there is by the poles of this equation. And then a similar equation can be written down for the effective mass of the molecule. That's much more technical. Here comes a comparison of this ansatz with quantum Monte Carlo calculations, which again, so these are diagrammatic quantum Monte Carlo calculations in which their claim is that they are summing up all orders of perturbation theory up to more than 10. So they are summing millions of diagrams, and their claim is that the convergence is perfect. And so the diagrammatic Monte Carlo results for these two ansatzes, these two different quasi-particles, the polar and the molecule, are given by the red and blue empty symbols. And the results given by this ansatz are given as these black lines. So this is the result. So what I'm plotting here is the energy of the polaron or the molecule minus the binding energy in vacuum, which is a trivial, which is giving a very large shift. So I'm already subtracting a very large shift from the data, and what you can see is that the agreement between the black lines and the empty and the solid and the symbols is incredibly good.
Excuse me.
Yes.
Should one expect that the transition point is completely smooth? So we mentioned it before. So these two ansatz, they're good on both sides, but exactly, so the question is, when you are exactly at the transition point, should this curve be smooth without a cast?
So maybe I said something wrong. I mean this. This results, the Monte Carlo results are exact to all orders.
Yes.
So the crossing remains.
So it's, if you would take derivatives, or something like that from both sides, is it?
So, but again, this is, these are two distinguishable quasi-particles. And indeed, this quasi-particle remains the ground state even when, remains a well-defined quasi-particle even when the other one has a lower energy. It gets a broadening, but it still remains a well-defined quasi-particle for a limited. So the two-wave function have the same number of particles, right? They have the same number of particles, but they describe two fundamentally different objects. So in one case, you have one impurity, so a fermionic object in the middle of a large Fermi sea, and in the other case, you have a tightly bound molecule, or a bosonic object in the middle of a Fermi sea.
My question is,
therefore, there could be an overlap between them, right? The terms in Hamiltonian that couple these two types of wave functions.
decay processes.
Yeah, so there are decay processes. So this object gets a width. So here the object, when it's no longer the ground state, it has a width, but it's still a well-defined quasi-particle. And vice versa, the polaron has a width here, but it's still a well-defined quasi-particle. So meaning that the imaginary part of its energy is much smaller than the real part.
If you ask the question a different way, if the calculation would just be a calculation of the true ground state of that system, you would have a smooth curve, right?
Yeah, that's the
So
question.
they're not, I mean, this.
But the question is, how do you compute the true ground state
So
of?
what the diagrammatic Monte Carlo does maybe is an exact solution for this given ansatz of a quasi-particle, but it's not an exact solution for the ground state of the many-body system, and this is why you have this.
Yeah, so what are the expectations? Is it exactly, if you look at the ground state of the system, so and look at the function of KFA inverse, is it supposed to have a completely smooth, or there should be singularity?
So, I mean, there are no trimers, so there is a so there should be this cusp, no?
Yeah, I mean, one of these solutions has an overlap with a bare impurity, and the other one doesn't. That's also how you can distinguish. So one of these curves, the polar one has a residue, and the other one does not have a residue. So it has no overlap.
The quantity has a sharp transition.
Yes.
Yes.
So this is what expected, right? Okay. Because you mentioned that it's smooth, so I thought that maybe it's.
No, okay, I was incorrect there.
Okay.
Sorry. No.
Okay. Thanks.
So okay, so how to just a few slides on the methods. So as I mentioned, to interpret the experiment, an important feature was, apart from the mass imbalance, was the fact that the resonance they were considering was narrow. So what do I mean by narrow? Sorry. It means that the scattering amplitude is not, the inverse of the scattering amplitude is not just a to the minus 1 plus ik plus r star k squared, where r star, you may be more familiar with this form of the way to write it. So minus r effective over 2 times k squared. But I write it in this form because it was introduced by Petrov in a paper some times ago. But what is interesting is that this quantity for basically in ultra-cold Fermi gases can be written as h bar squared divided by 2m r a background delta b delta mu. And this quantity is generally positive, and so that's easier to deal sometimes. And okay, there are two possible definitions of a narrow or broad Feshbach resonance, depending on whether you come, let's say, from the few body or from the many body world. So if you want, you can define that a Feshbach resonance is broad if this if r star is much smaller than the van der Waals length. If you're interested in few body physics, because this means that in a few body collision, this term here will be negligible. But in a many-body system, especially in a Fermi system, I mean, momenta of the collision are of order of kf, or important momenta are of order kf. So in a many-body system, it makes more sense to compare r star with kf, rather.
Star, the minus one have a effective range?
Sorry?
Is r star minus one have an effective range? Because if that's
Yes.
if it's minus one have the effective range, it should be comparable to the van der Waals.
Yes, it is. I mean,
so it cannot be much smaller than van der Waals.
Not
But-
necessarily. Sometimes it can change. It can happen when you're in between states.
I think it's.
No, the effective range can change sign, and they can go to infinity.
Yes.
It depends.
Fokker had some formula for this effective range in units of.
They should be of the same order.
But it depends. So this can be any. I mean, in the vicinity of a Feshbach of narrow Feshbach resonance, which is the case for many. So basically, when the coupling is very weak between the molecular state and the bound.
I have to say that Petrov probably he did not say that r star is minus one half of the effective range. It's only minus one half of the effective range in some cases, but not in more cases.
Okay, let's say this is the way in which people are used to see it, but maybe, I mean, there are two different objects. One is yes, I agree with you that is not the effective range. I mean, this formula is correct in the vicinity of a Feshbach resonance, let's say. Where also, I mean, you would expect also that A is of order the van der Waals range, correct?
Even for Feshbach resonance, the effective range is not much smaller than the van der Waals range.
For broad resonance, or
That's not true. The speaker is right.
Okay, good, thanks. Okay, I will show you actually how this arises if you want.
Now, on the previous slide, when you showed the diagrammatic Monte Carlo, they were done for broad resonances.
That's correct, yes. But actually,
no relevance to this part.
no, but actually you can show that the narrow resonance is actually a weaker coupling link. I mean, the broad resonance limit is obtained when the coupling. Let me finish, please. Let me finish, please, okay? I'm saying, okay, so a broad resonance is the case in which the coupling is strongest between the molecular and the atomic channel. So this is a confirmation that this model works for a strong coupling case. A narrow resonance is actually a case in which the coupling is weaker because R star is proportional to 1 over G squared, where G is the coupling between the atom and the molecule. So what I will show is that, so one can expect, and actually one can show that for a very narrow Feshbach resonance, the results become completely analytic. So this is a confirmation the system works in the strong coupling, and in the weaker coupling, you can just expect that the agreement is better. So, and as I will show, the agreement with the experiment is perfect. So what happens when Feshbach resonance is narrow is that, if you want, here is a plot from the experimental situation in Innsbruck. So this is as you see, the scale here is in milligauss. So there is a Feshbach resonance. This is the scattering length, the blue line. Here is the pole of the resonance. And this is the two-body picture in which you have, this would be the energy of a molecule at a broad resonance, so 1 over ma squared. But this is actually the energy that they can measure. So what happens is that in the vicinity of a narrow Feshbach resonance, one can write still the molecular energy in terms of 1 over a squared, but a is now a star, which is related to the usual scattering length, but also R star enters in the formula. And in the vicinity of the resonance, when a is much larger than R star, then a star is equal to a. So the molecular energy is still quadratic in this region here. But when you go far away from the resonance, the a star becomes square root of a times R star. So this means that the molecular energy here becomes linear, if you want.
So a star, this is just the solution of the pole of the scattering amplitude up there?
Correct.
Okay, so this is what nuclear physicists would call gamma.
Okay, so my knowledge of nuclear physics is very, very limited. But yes, this is the pole of the scattering amplitude, correct.
So what kind of definition? You mentioned there are two definitions. So in which sense you are narrow? In the few body or in the many?
So let's say the experiment is in the range where Kf times R star is 0.9, okay, where R star is defined by this formula, and Kf is just given by the density of the gas.
So it's narrow in the many body sense, and what about the few body? So is the other thing satisfied as well?
R star is much larger than the van der Waals as well. Yes, because
much small.
R star, so much larger, so the Feshbach resonance is narrow.
Both definitions are fulfilled.
Both.
Actually, I mean, the many-body definition is that 1 over k of R star is a small parameter, and here is of the order of 1. So
yeah. Okay. It's not that.
But the point is that the many-body physics becomes completely perturbative if kf R star is very large.
So
1 over kf R star is small.
Okay.
So what I will be I mean, in this experiment you were correct. So it's not a narrow, it's not broad either. So the results are very, very strongly influenced by the fact that Kf R star is of order 1. So, but the experiment is not in the regime where the resonance is extremely narrow. Also because you can see, I mean, they have narrower resonances, but then the stability required in magnetic field becomes incredible. So here they did they built the machines so that they have 2 milligauss, I think, or 5 milligauss stability in magnetic field. But if you go to even narrower resonance, then the requirements on the Feshbach stability, stability of magnetic field become extreme. Okay, how to address a problem which you have many body physics and narrow Feshbach resonance, and eventually we included also the background scattering, which can be important in some of the problems, like for example understanding the cesium, the very early cesium paper on Efimov physics. The scattering length was very large. So to do that, we wrote the T matrix, which describes the scattering between up and down spins in terms of an open channel T matrix and a term that couples open and closed channels. So the first term, the open channel, the terms describing open channel only collisions, has the form of 1 divided by a renormalized collision. T background, which basically describes a single renormalized collision, and then you have to subtract from this the pair propagator, which has this form, and medium effect come in here through the Fermi functions. So the Fermi function for the spin down, which basically is, can be always taken as 0 because there is only one impurity. But the many body effect in this problem enter here through this Fermi function. And and the pair propagator is correctly renormalized, so it doesn't diverge at infinity, and this allows you to express this object in terms of the renormalized scattering length for the background channel. So for the coupling, when you have scattering between the open and the closed channel, so what you can do is write down this piece of the T matrix, which contains 3 terms. It contains the coupling between the open and the closed channel, which is a Bayer coupling plus some scattering events in the open channel, and then finally formation of a molecule. Then you have a propagation as a dressed molecule, which is described here as propagation of a Bayer molecule, plus self-energy basically for the molecule, which contains eventually the molecule splitting up and interacting in the open channel and reforming a molecule at the very end of the process. And this can be, these are the formulas. And again, these 2 terms can be summed up. And one obtains a very nice and simple formula for the T matrix in presence of a medium and in presence of a large, eventually background scattering. And as we'll see, this contains also the effect of a narrow Feshbach resonance. So one can write down the T matrix in this form, which would be the standard one, except that we have written it in terms of an energy-dependent quantity, which has the form of a scattering length, but it contains here the energy in the center of mass of the 2 particles. And now, if you do a low energy expansion of this object, and in vacuum, what you obtain is basically there should have been a k squared here, sorry. But what you obtain is the correct scattering amplitude in vacuum. And from this formula, you obtain that A is equal to A background times 1 minus delta B divided by B minus B naught, which is the standard formula.
A star should be multiplied by k squared, or?
There should be a k squared here, yes. Sorry, I forgot that. Yes, correct. And here you see that R star is actually the value given by Petrov, the one I was having in the previous slide, times a factor that actually can diverge up to infinity, as Aurel was saying. So as Aurel was saying, this is the value at resonance, but it's modified away from it. And in particular, it diverges when A goes to 0.
Can you explain a little bit more why it depends on the center of mass of the pair, or is this maybe I misunderstood what E is?
Yes, so ECM is, if you want, the P squared over 2 is P squared, the total momentum flowing through the diagram, divided by 2m, where m is the total mass of the particles. So if you want 2m up plus 2m down. So this is basically the energy of the molecule. So here you have
When you say total mass, can you say total of what?
Yes, it's spin up plus spin down. So it's the mass of the molecule, if you want. So if you want, you see the ECM is what enters in the propagator of the molecule. So is the energy of this molecule here, if you want, the kinetic energy of this molecule. So it's capital P, the total momentum flowing through the molecule squared divided by 2, the mass of the molecule. Okay. Okay, this is okay. So coming to I see that time has flown by. Coming to how we observe this. So.
I was thinking it came from these Boltzmann distributions that you have in there, but it's not.
No, they were Fermi distributions.
Sorry.
No, it doesn't come from. I mean, that's there even in the vacuum.
So there is no effect from anybody.
Not.
In these equations.
I mean, there is in the pair propagator. So the many body enters here, but as you see, it also enters here and here. So the many body effect come in here, here, and here. Okay, the many-body effects are, are Pauli blocking effects in the open channel, if you want. But since the molecule can split up and propagate as free particles in the as intermediate events in the open channel, the Pauli blocking effects renormalize also the molecule. Okay, so how to observe this? The main tool for this experiment has been RF spectroscopy. So what one does is, what they did in the experiment of Innsbruck is they started from potassium impurities in the 0 state, and they used RF transitions to flip the particles into a 1 state, a spin state, which we term by 1, in which the potassium impurity is strongly interacting with the lithium gas. So in state 0, the potassium impurity have 0 interaction with the lithium gas. So there are no, if you want, initial state effects, which were what you were saying the other day, final state effects in earlier systems. In earlier states, in earlier experiments, they were doing the opposite process. They were starting from strongly interacting state, and they were flipping into a weak non-interacting state. But actually, they had strong interactions even in the final state. And that was perturbing quite a lot the measurements. But here they started this Innsbruck experiment. They went into ideal condition in which the initial state is completely non-interacting. So by this process, you're actually probing directly the spectral function of the system. So you're taking one particle and throw it in a many-body system in which it interacts strongly. And this is what they observed. So if you go to low power, if you use RF low power, this is the Feshbach resonance. So this is the pole of the resonance, and the little white lines describe the strongly interacting regime, where this is smaller than 1. So they see nicely that there is an attractive branch and there is a repulsive branch. And the two energies match very nicely with the theoretical prediction, which are the lines I showed you before. And, okay. Sorry. So they apply a radio frequency transition with a certain energy, and the colors indicate the transfer efficiency, or the number of particles transferred from the initial to the final state. So if they are detuned from any excitation, there is 0 probability of transferring a particle. So if you want, so they're measuring how many particles they transfer, and this is a direct measure of the spectral function of the system. And now, but if you remember, there was supposed to be something here in the middle, and this actually comes out when you do high power radio frequency spectroscopy. So there you're really able to measure that there is something in the middle. So now at high power, the signal coming from these two lines here, it's no longer meaningful because the transition are completely saturated. But here in the middle, there appears a clear continuum. And the reason for which it doesn't appear at low power is that the two wave functions are very different. So the overlap between the initial state, which is a single particle state, and the final state, which is a molecule, it's very small. So you need a high power radio frequency spectroscopy in order to transfer particles into this state.
So you say you find there is some small overlap because you need high power, but in your calculation, the overlap between the two states is 0, right? Between the molecule and this attractive polar one, at the level of your calculation.
Yeah. So yes, but so this coupling is what to say.
It's non-zero. In his calculation, it's non-zero because this wave function cannot be orthogonal.
Mm-hmm.
Here they consider overlap between non-interactive state and interactive state. And when they calculated, they were speaking about overlap between molecule and polar states. They are different.
Yes,
There's
that's
no
correct.
relation. Yes?
Yes, that's correct. So here we're starting. Okay. So by putting a lot of power in this radio frequency transition, they are able to populate this state here. So they populate in both. I mean, if you want, the spectral function is a single particle property, so it includes only So in this, if you sorry, in the spectral function there are both excitations present. But if you were to plot the spectral function from, I mean, even from the polar non-ansatz, there is a continuum. In the polar non-ansatz, there is a continuum, which is, on the other hand, is always an excited part. So there is a ground state excitation, and there is a continuum above the ground state excitation. And instead, the molecular solution has this continuum here always. And by using this RF, you're probing overlap with both wave functions, basically.
How we quantify this power of RF? How it's
Oh,
different between low and high. So
I think it was a factor of 10, but 5 or 10.
Intensity?
In intensity, yes. It's the intensity of the radio frequency. So the frequency is fixed by the vertical axis, and it's just the power you're changing, yes. Okay, and as I was mentioning before, so this is a ground state of the system. So it has if you want to you see that it's a very narrow line. So it has basically 0 width and 0 decay. But you can see that this line here gets broader and broader, and this means that the excitation gets a larger decay. So we've been investigating this decay. So we've been investigating the lifetime.
Maybe we can.
Yeah. Okay. Thanks. So we have been now investigating the lifetime of this excitation here, just looking, staying for a fixed, for a variable amount of time at a fixed scattering length, and checking basically gamma, the decay rate of or the lifetime, or if you want, the decay rate of this quasi-particles. And we see that this is gamma, so it's the inverse lifetime. So the lifetime is very long away from the resonance, where the particle become, if you want, the continuum or the excitation and negative energies are very far away. So here the lifetime is very long, but as you approach resonance, the lifetime decreases rapidly, or if you want, the decay rate increases rapidly. And the blue line and the red line are two calculations we did for the red line is decaying to this shaded continuum, while the blue line is a decay into this polaronic state, which, as I was saying, has 0 width until it hits the continuum, and then it gets a broadness or a width as it enters the continuum. And so there is some two-body process or three-body process that brings you down into this continuum, and there is a many-body two-body process. I mean, it's a two-body process in the sense that this excitation goes into this excitation here, but it's only allowed in a many-body setting, which gives the blue line shown above there. And so one expects that the total lifetime or the total decay rate would be the sum of these two processes, and in particular will be dominated by the largest one. And that's very good agreement with the experiment again. So now coming to as I was saying, the coherence properties of these excitations can again be probed by Rabi oscillations. And so again, what we're looking is applying a radio frequency between a non-interacting and a strong interacting state. And but now we're just performing cycling. I mean, keeping the RF on for a long time, and observing the frequency of this Rabi oscillation. So what does the Rabi operator do? It's with a certain frequency flips particles from the non-interacting state into the strong interacting state, and vice versa. The weakly interacting state, the initial state, is just a Fermi C plus an impurity at 0 momentum, and but which doesn't interact with the Fermi C. And the final state is the Fermi C plus an impurity at 0 momentum, because the radio frequency does not change the momentum of the particles. So in the strongly interacting state, 1, and this happens with a certain amplitude, square root of which I call square root of z, plus the excited part, or if you want, the quasi-particle dressing. And the Rabi operator probes directly only this part of the wave function. So in particular, if you take this overlap here, you get omega 0 times square root of z. So if you now measure the Rabi frequency omega that you can actually measure in the experiment divided by omega 0, which is the Bayer transition frequency. I think, yes. What you're actually measuring is directly square root of z. And I write it as square root of z because this z is actually what I defined at the very beginning as the residue of the quasi-particle. So it's basically, as you can see here, square root of z is the overlap between the non-interacting and strong interacting particle. And so the measurements, the blue and the red dots are measurements, and the lines are the theoretical lines extracted directly from the theory. Yes?
And this was all done for 0 temperature, so if you have a finite temperature, you'd expect to have less coherence, but I guess temperature is small compared to something. So what is the for the small temperature?
So I think my colleague Georg Brunner now has been continuing looking at further into this, and I think they've been considering finite temperature. For the moment, I mean, in the work I did, we didn't include finite temperatures, but I agree with you that, I mean, the temperature here is very small, and indeed we could not see any trace of the temperature, and but definitely the temperature will destroy coherence. Yes. Small compared to the Fermi temperature? Yes, so the Fermi temperature of the majority is about 0.1 TF. So the temperature of the majority is 0.1 TF. And there are very few impurities, so which are in thermal equilibrium with the majority. Okay. Okay. See, my time has been running. Okay. Maybe I will just kind of finish with a couple of slides. I see I managed only to cover my first part of my talk, but I just wanted to arrive to something that I discussed with Sheena some time ago. So this will be 2 or 3 slides at most. So I wanted to say, as I was saying at the beginning, the equation of state of this imbalanced Fermi system can be actually obtained by looking at the properties of Fermi gas, of polar ions or quasi-particles. Because if you want, you can write the equation of state or the energy of the system as basically a non-interacting Fermi gas, which is composed of majority particles. And then the minority particles are basically can be treated as free quasi-particles. So, but you have to take into account that they have a different mass. So this takes into account the fact that the mass of the quasi-particles, the spin downs, is renormalized when they form these quasi-particles. And then there is this binding energy here, which is the binding energy of the impurity with the cloud. And then correction can be shown to be very small. So this equation of state, actually, it's obtained from the property of a single impurity in a Fermi gas, but actually can be shown that it's quite accurate up to about 30% of impurities in a Fermi gas. So even though it's a one particle calculation, I mean n+1 problem, it actually gives very much insight up to about 30% of impurities. Yes, but in the regime where the molecule is the ground state, you can replace this. I mean, you can write basically a similar equation of state. Except that, I mean, when you have a finite number of particles, you have to be careful about phase separation, as also Sheena was pointing out. So there is at some point, I mean, for large density of impurities, there is a phase separation appearing in the system. So you have to be careful in which regime you apply this equation. Okay, so one can ask the question, how many spin-ups are attached to a spin-down? And this can be figured out by a nice argument that I applied many years ago in my first project with Chris Pettick in looking at how many particles can be attached to an ion in a condensate. And a similar argument can be applied here. So how many spin-ups are attached to a spin-down? To find this number, what you require is that the density of the majority atom away from the impurity should remain unchanged when you add a single impurity. So you ask that the chemical potential of the spin-up remains unchanged when you add a spin-down. So the chemical potential of the spin-up is the derivative of the energy density with respect to the n-up. And now you ask that this is unchanged when you differentiate with respect to n-down and with n-up. And here is the number of particles you have to add to the cloud.
Did you also look at the mass of the particle, or is that the same?
The mass of the quasi-particle?
Yes.
It's not the same. So if you want, what you get is that the effective mass, so this is the results of this calculation, and what you get is that, I'm plotting here, so the effective mass of the quasi-particle actually diverges when you go past this transition. And also the effective mass of the molecule diverges when you go past this point, while this quantity do not diverge. So they are not the same quantities. Okay, where the divergence of this quantity actually signals that it's an instability in the system, basically. While, I mean, this calculation does not show any instability. Okay, so this tells you that the number of particles attached to the impurity is positive, because here I'm plotting a minus sign. So it's a number that is, it's about close to 1 for the attractive polaron. It goes to 0 here. But you can see that in the regime of strong attraction, the polaron is not able to bind one particle, which is the result you would expect. But this is what the molecule is able to do. So the molecular ansatz recovers the correct result that to each spin down there is attached a spin up. This is the result, while this cannot be done by the by the polaronic ansatz. So if you want, this gives some insight of why there is the need for, let's say, 2 different ansatz. And the repulsive polar instead is pushing away particles and can push away almost 1 particle before it becomes basically unstable. This is the result for equal masses and broad resonance.
Just can I turn it? So if you would plot the same from the mass, how would it look like then? Is that maybe these gray lines? Lithium is so much lighter than potassium, right? So
yes, I don't. So this is the result for equal masses and finite and 0 range. What you wanted the effective masses?
I understand the difference between these 2 definitions of.
Okay. So do you remember? No. Okay, it's been a while. I haven't looked at that. But so what I remember is that the effective mass of the polaron sits to 1 in the regime where the polaron is well defined, and then it's so here the effective mass of the polaron is 1, and it diverges. It's about 3. It's similar to the effective mass of the molecule. It's about 3. Actually, they're very close together. So it's 1 here. It goes to 3, and then it diverges when you go through here. So if you want what you would usually plot is indeed actually the inverse effective mass, because that's related directly to the derivative of the energy. And the effective mass of the molecule is 2 in this regime here, and then it's about 3 when it comes here, and then it diverges here. I hope this answers your question. Sorry, 1 means the mass of the bare impurity, and 2 means the mass of the total molecule, so spin up plus spin down. So if you have lithium and potassium, that would be the mass of spin up plus spin down. Yes.
And what is the effective range of this polaron? How big is the cloud in terms of?
That depends a bit on how you define it. So the cloud is.
I'm asking because you talked about reduced dimensionality. So does confinement has any effect? So if you start reaching the range where the polaron is the order of the confining trap.
That's an interesting question. I mean, did you look into that? So they are the experts in polarons in quasi-QB and or reduced dimensionality. So the problem is that the polaron cloud is very large. No, it decays. It's a Friedel. I mean, you can see it as the polaron induces Friedel oscillations in the Fermi sea. So there are oscillations, and these go on very, very far away from the cloud.
But what we found was that this attractive polaron approaches. So we started from a 2D theory, and then we introduced a harmonic confinement in the 3rd direction. And what we found was actually as soon as the Fermi energy of the majority particle is comparable to the trap frequency, you basically already recovered the 3D limit, which is kind of interesting. That already, when you would think that you're still quite 2D-like, you're in the 3D limit. So I guess that could say something about the size of the polaron being as soon as your confinement length is comparable to your Fermi or your interparticle spacing, then you have a 3D situation.
Okay, so last slide on the contact for an impurity. So you can compute the contact of an impurity from the derivative of the energy density with respect to 1 over A. And this, since the energy density, just neglecting the effective mass of the impurity, this is basically just the derivative of the energy of the impurity, the polaron energy with respect to 1 over A. And this gives this plot here that was already shown by Punk and Zwerger. So this is the contact for the repulsive polaron. This is the contact for the molecule. And this is what we computed the contact for the this is the attractive polaron, this is the molecule, and this is the repulsive polaron. And so what I found were two interesting relations. One is the link up between the polaron, the contact of the polaron and the energy of the polaron and the number of particles entering in the polaron cloud. And so one can show that this relation holds. And this relation has a nice feature that since the contact remains finite at unitarity while A diverges, this means that at resonance the number of particles in the cloud is equal to minus E down divided by EF, so minus the polaron energy divided by EF. And this number is always a number of order unity. So in the case of equal masses and broad resonance, this is 0.5 or 0.6. And the other nice result, so when I found this, I said, oh, maybe I found a new tan relation. But then I spoke to Sheena many years ago at a BEC conference in San Feliu, and maybe the day after or even less, he came back saying, oh, but actually your result can be derived in terms of the tan relation for pressure. So this can be seen, okay, if you write the pressure of an ideal Fermi gas is this. So if you change the density of an ideal Fermi gas, the change in pressure is equal to 2/3 delta N up, so the change in density times EF. And now if you keep the number of particles fixed, so you can imagine that if you're, for example, forming an attractive polaron, some particles are drawn together by the impurity, so the overall pressure in the container is reduced by the fact that some particles are bound into the impurity. So the delta N up, so the change in the density is equal to minus the number of impurities times the particles of the majority that are bound to the impurity. And so by working out the math, one recovers that this relation can be written in terms of this one here. And now if you add the contribution from the non-interacting Fermi C, you find the Sheena's pressure relation. Okay, I see I've managed to cover only 2 of the 3 topics, but I probably should stop here, and thank you for the attention.
In view of the time, I also suggest that we delegate all questions to the discussion session at 3:30.
Okay, thanks a lot.